We have seen the MSNE characterization result in the previous module, and even before proving that, we have actually used it to find the MSNE of a game, of the goalkeeper and shooter game. Now, let us use this theorem to develop an algorithm in a more formal way. It is essentially the same algorithm that we use to find the mixed strategy Nash equilibrium of the penalty shootout game, but written a little more formally. So we are starting with a normal form game as given here. And the first thing that we'll have to do, because the characterization theorem is saying everything on the basis of the supports, we'll first have to fix the support profile, and we'll have to iterate over all possible support profiles. That's the way this algorithm works. So if we go over all possible supports, so suppose for player 1, the support is x1, for player 2 support is x2. So therefore we'll for this support profile from x1 cross x2 to xn, we are going to develop a feasibility program where the variables are the probability masses over those strategies in that support. So what does that mean? Let us go over step by step. So sigma Sj, so if we pick a specific player J and we look at the strategy of that player J, which is living in that support, so let's say this Sj is in capital Xj, which is the support, then we are going to define the sigma and J Sj as a variable in this feasibility program, which essentially says that what is the probability we are associating with that strategy. So with what probability this player is going to play that strategy. Now, what we have seen in the previous module, the characterization theorem says that for all the strategies which are in the support for this player, the expected utility for this player will be same. So therefore, we can write, so this is essentially a so we are here looking at the player I. So for player I, all the other players, that is j not equal to I, we are multiplying their probabilities of picking their respective strategies. And this essentially is the expanded form of sigma minus I, s minus I, this one. And multiply that with the utility when this player is playing this si and the other players are playing s minus I. And when we are taking the sum over all s minus i's in capital S minus I, note that these are all finite sets, so we can take the summation. This is giving us the expected utility. So this whole right hand term together is nothing but ui of si sigma minus I. We have just written it explicitly so that we can show the dependencies on the individual variables in this feasibility program. And this should be equal to some variable, let's say wi, and this will be true for all si which are living in that support xi. So here we are considering player I, its support is xi, and this equality should be holding for all players I in n. So this is essentially the condition 1 of that characterization theorem. Similarly, for all the strategies which are outside this support, so si minus xi, we have this wi, which is the value, the expected value, that should be at least as much as the expected utility for any strategy that is living outside this support. So this is essentially just writing out the same two conditions in a more expanded form. So this is condition 1 of that characterization theorem, and this is the condition 2 for characterization theorem. The rest of the conditions are nothing but the feasibility things. So essentially all this sigma j sj are probability masses, so therefore they should be non-negative and they should sum to 1. So this feasibility program is solved for one support profile, and exactly this is the procedure we had followed to find out the mixed strategy Nash equilibrium for that penalty shootout game. We have actually started with different support profiles, and we have seen that for certain support profiles you cannot maintain this feasibility. I mean, there is no solution to this feasibility program, so we throw that out, and whenever it was possible, we found out the corresponding values of the sigma j's, sj's for all these players, and that happens to be the mixed strategy Nash equilibrium for that game. So we'll have to iterate over all these possible support profiles, and there can be a very large number of support profiles because this xi, so x1 for example, can be all possible non-empty subsets of the strategy set of player 1, which is S1. So it can take this many number of possible values, 2 to the power cardinality of S1 minus 1. And similarly, the whole support profile therefore will be the product of all these terms. So this algorithm is not really the most efficient algorithm, and in particular this feasibility program, if you look at even for a specific profile of supports, that feasibility program is also not a linear program unless there are only 2 players. So if there are 2 players, then this number is essentially a linear, so there is only one such variable there. Otherwise, all these variables, sigma j, sj's, are products, are appearing in this expression in a product form. So therefore, it's a non-linear program, so which is not very easy to solve. But the bad news is that there does not exist any polynomial time algorithm for general games which has more than 2 players. In particular, the problem of finding a mixed strategy Nash equilibrium is what is known as PPAD complete. This is a specific complexity class, and we are not going to discuss too much about it. The name PPAD stands for polynomial parity argument on directed graphs. If you are interested, you can search about it and find out the complexity class. But the problem of finding a mixed strategy Nash equilibrium falls inside this class, and it has been shown by these people, Daskalakis, Goldberg, and Papadimitriou in 2009. All right, so with that, let us now come to that type of algorithm where you are removing the dominated strategy. So remember, for finding pure strategy Nash equilibrium, we were just removing the dominated strategies, the purely dominated strategies. We are going to use a very similar thing, but now we have the flexibility of removing those strategies for players which are dominated by a mixed strategy of the same player. So earlier we were just looking at the domination by another pure strategy, but now we can even talk about mixed strategies, the mixture of 2 or more strategies essentially giving rise to the dominance. So in this game, so let us look at this specific game here. Can we actually see some kind of a dominated strategy here? Definitely we cannot find any purely dominated strategy. So let's say if we look at player 1, none of these strategies T, M or B dominate each other. Similarly, for player 2, there is no strategy which purely dominates the other strategies. But if you look at this strategy, so where you are picking half, so this strategy T with probability half and strategy M with probability half, then you are taking the mixed, so the expected utility that this player is getting when it's playing half and half. So 4 and half, this will be 2.5. And if you take this expected utility, then it will be 6 plus 2 times half, which is 4. But that number actually, that mixed number is larger than this 3, and that mixed number is larger than 2. So therefore, half T and half M, this mixed strategy actually dominates B. So this is a observation that was not possible, that we did not consider when we discussed about this kind of games, because in pure strategy Nash equilibrium we are trying to find the pure domination of the strategies by another pure strategy. But here we can actually do that even for mixed strategies. So what we can say formally is that if a pure strategy SI is strictly dominated by a mixed strategy, let's say sigma I, then in every mixed strategy of that game, SI is chosen with probability 0. You can take a look at the standard textbooks to find this proof. However, the intuition of the proof is very much similar. So because now we are in the mixed strategy world, we can actually think about the domination by a mixed strategy. And because we have some strategies which are strictly dominated by a mixed strategy of the same player, then we can, without loss of generality, remove that strategy. As if the player, whenever it was thinking about playing that strategy, it can always strictly improve its payoff by choosing the mixed strategy which has dominated it. So therefore, there is no reason why it should be picked, and a mixed strategy Nash equilibrium will never choose that. This theorem essentially formally proves that. However, there is a good news about mixed strategy Nash equilibrium, and that is by a result due to John Nash in 1951, which shows that every finite game has a mixed strategy Nash equilibrium. What does that mean? The finite game, that means the number of players and the number of strategies for each of these players are finite. Now this proof is not very difficult to do. At least we can do it for 2 players and show it very easily. But I'll not spend time to go over the proof in the module itself. Rather, I'll post a note where where each of these steps you can read about it. But to read that note, there are certain ideas, some mathematical tools that will be needed, and some results that will be needed from real analysis. That is what I'm going to explain in the rest of the time. So the first notion is about convexity. I am sure that you know what a convex set is. So a set, and here we are only dealing with subsets of r to the power n to keep things simple. The definition of convexity is even general, but we are only looking at an n-dimensional real space. So it is convex if for every x and y that lives in this space. So if we look at a set S, for every 2 elements, if you join the chord between these 2 points, that is going to always live within that set. So to give an example, so let us look at a 2-dimensional plane, and let us look at a specific set which looks like this. Is this a convex set? The answer is no, because you can always pick some x and y here, where if you take some convex combination, so if you take a combination of these 2 points and you go to a point which is lying outside the set, that violates the definition of convexity. So therefore this set is not convex. So what will be the shape of a convex set? Something like a circle or things which does not have such kind of situations where if you draw a chord between 2 points in that set, that goes outside the set. Okay, so the second property, the second definition is about closedness. So we say that a set is closed when it contains all its limit points. So what does a limit point mean? So limit points are those kind of points for a set where every neighborhood of that set contains a point in S. So let us think about this. So suppose I have a point and we are going to define this as a limit point. If you draw any arbitrarily small ball around it, let's say we are still living in the 2-dimensional space, so I draw a small circle with a radius epsilon, and this epsilon can be arbitrarily small. It just requires to be positive, but it can be arbitrarily small. And for every such circle, no matter however small it is, so you will have some points of S that lives within that. So one classic example for a limit point of a set is when the set is, let's say, 0, 1 open. When it is open on this 1, it means that it does not contain 1, but all the numbers which are arbitrarily close to 1 that lives inside this set. Now we claim that 1 is a limit point to this set because if you have this real line where it is closed at 0 but open at 1, that means if you are sitting at 1 and you draw an arbitrarily small circle like this, then every such circle will have some point which is living in this 0, 1 open interval. Think about it, and you'll see this. This will take some time to sink in, but the point that I'm trying to make about these limit points is quite easy to follow. So once we have such limit points, we'll not call this kind of a set 0, 1 open to be a closed set, because there exists some limit point. So here the limit point is 1 of this set, which is not contained within that set. So if we instead had 0, 1, which is closed, that is, we also include the point 1 into this set, then it becomes closed, and there does not exist any other point which is a limit point, and that is not inside this set. So that is one important notion. So we need this property of closedness. Boundedness is very simple. We already know by the term itself, we know what a bounded set is. So what does it say formally? We will say a set to be bounded if there exists some point x naught in R to the n. Notice that this x naught need not be inside this set S, and some finite r. So this should be larger than 0 and should be smaller than infinite. So it is a finite radius r, such that if you look at every point, so for every x that is living in X, if you take the difference between the distance between x naught and x, and we are just looking at the L2 norm, that should be smaller than r. So let's say we have a set S which is looking like this. It is in let's say it is in R2 again, two-dimensional plane, and suppose there is x naught, and there is a x naught and there is a radius, let's say r, and then you can draw this circular ball around this x naught point. All the points that you can pick from this set S, the Euclidean distance between x and x naught will be bounded within that R. So if we can do this kind of we can ensure this property, then we say that this set S is essentially bounded. Now you can play around with these properties. You can see the conditions where it is convex but not closed, closed but not convex, closed and convex but not bounded, and so on. You can actually create examples of all sorts, and that will essentially make your understanding better. Now we are going to call a set to be compact if it is closed and bounded. So we are just using the fact that we are living in this R to the n. So these are only real spaces. So there is a different definition of compactness when it is not R to the n. But since we are here, it's easy. So every set in R to the n which is closed and bounded, that is also compact. So that's what we are going to use. Now a result from real analysis that we are going to state, and this result will be very much useful in proving the Nash theorem. This is called the Brouwer's fixed point theorem. So what is a fixed point? Fixed point is nothing but a point where a function gets mapped to the same point where it started from. So let's say we have a function which is starting from x and it is mapping to x, the same set. Then if there exists some x which when you apply f to it and get fx, that value is nothing but x itself. So if you want to draw a figure in 2 dimensions, this is nothing but and suppose we have a function like f of x. So on the y-axis we are plotting fx, and on the x-axis we have x. Then what a fixed point is saying is that it is the point where it is crossing this y equal to x line. So this point here is a fixed point, because at this point, whatever that x, let's say x star is, the value of that fx star is nothing but x star itself. So therefore, we call that point to be a fixed point. Now, this Brouwer's fixed point theorem is saying that if you have a set S that is convex and compact, and if you have a function which maps that set into itself, and the function is also continuous, then it says that T has a fixed point. So that means that there exists some x star in S which maps, which is getting mapped to itself via this function Tx. We are not going to prove this result. This proof is a little complicated. Rather, it's already a very well-known result. But I can give you an illustration of this result in 2 dimensions. So suppose we have a very similar thing. We have t on the y-axis, t of x, and we have x on the x-axis. And we know that this function is, so suppose it is mapping some interval here, so 0 to m or something, this interval into itself. So on the y-axis you also have 0 to m. Now this function looks something like this, maybe like this, and this result is saying that you can always find some point which passes through this y equal to x line. And that you can clearly see that this is definitely going to be possible, because this is a function. It has to give some value at each point from 0 to m, and because this is continuous, can you ever draw a function which does not pass through this? You can't, because this is like a box, and you are going from one point to another, and try out different ways of drawing a continuous line on this which has values from every point from 0 to m. You can never find any point which does not pass through y equal to x. Yes, if it was a discontinuous function, then you could have drawn something like t equal to t is of this value here, and then after that it changes its value. So in that case, it might not intersect with that y equal to x line. But as long as the function is continuous, this fixed point is guaranteed to exist. And the Brouwer's fixed point theorem is essentially saying that.